the expression of Vc of t for different values of S1 and S2, we discuss three possible cases. For example, in case A, when the roots are real and distinct, we say root S1 is minus alpha 1 and S2 is minus alpha 2, where the two roots are real and have different values from each other. Then the expression of Vc of t becomes pretty straightforward, that is, by inserting the value of S2 and S1 in this expression, we get an expression like this. In such an expression, we can see that the value of Vc of t is equal to a constant multiplied by e raised to the power first root S1 t plus another constant k2 multiplied by e raised to the power second root of characteristic equation multiplied by t. So in general form, expression of Vc of t in case the roots are real and distinct is regarded as Vc of t equal to k1 constant e raised to the power s1 root times t plus k2 constant e raised to the power second root times t. In case B, when the two roots of the characteristic equation are equal and repeated, that is minus alpha, simply inserting the value of S1 and S2 equal to minus alpha generates an indeterminate form, that is 0 by 0 form, as is visible from this expression. In order to solve such a 0 by 0 form, we put S1 as equal to minus alpha and S2 equal to minus alpha plus x, where x limit x approaches to 0. Then the expression for voltage across capacitor becomes this one, and after doing the mathematical manipulation we come across with a closed form expression like this. Here in this expression as well, we can see that 1 minus e power xt over x as limit x approaches to 0 generates a 0 by 0 form. The application of L'Hopital's rule on such an expression gives us minus t as a result. The L'Hopital rule is applied in such a way that we have to differentiate the numerator with respect to x as well as the denominator with respect to x as limit x approaches to 0 in case we get a 0 by 0 form. So differentiating numerator with respect to x generates minus t e raised to the power xt, and differentiating numerator the denominator with respect to x also generates 1. So when limit x approaches to 0, we get minus t e raised to the power 0t over 1, which becomes equal to minus t. Hence, we get an expression of Vc of t as to be of this form, where this 1 minus e power xt over x is replaced with t. As can be seen from this expression, that voltage across capacitor now is a constant multiplied by e raised to the power root times t plus another constant times t times e raised to the power root times t. So in case when the two roots are equal, then we have a general form of expression for the solution of second order differential equation as equal to k1 constant e raised to the power root times t plus k2 times t times e raised to the power root times t. One last case, when the roots of the equation are complex conjugate, that is S1 is equal to minus alpha minus j beta and S2 is equal to minus alpha plus j beta, then we have simply putting the values of S1 and S2 as to be minus alpha minus j beta and minus alpha plus j beta leads us to this expression. And simplifying this expression gives us this expression, where we can see that e raised to the power j beta t plus e raised to the power minus j beta t over 2 can be manipulated mathematically using Euler identity to be in the form of cosine of theta, whereas e raised to the power j beta minus e raised to the power minus j beta over 2j can be replaced with a sine of theta as is manipulated from the Euler identity. Then the expression for voltage across capacitor becomes v naught e raised to the power minus alpha t cosine of beta t plus alpha v naught plus alpha I naught over c over beta minus e raised to the power minus alpha t sine of beta t. Remember, the value of alpha and beta are basically obtained from the roots of the characteristic equation, which are regarded as minus alpha minus beta j and minus alpha plus j beta. So in general expression, we can write it in the form of k constant e raised to the power real part of root times t cosine of imaginary part of root times t plus constant k2 times e raised to the power real part of root uh, times t plus sine of imaginary part of root times t. So in general, it can be written as constant e raised to the power real part of root times t multiplied by cosine of imaginary part of t root times t plus another constant times e raised to the power real part of the roots times t multiplied by sine of imaginary part of t when roots are complex conjugate in the form of minus alpha minus plus minus jp. So this is the summary which should be on your fingertips throughout your life whenever you are asked to solve a second order differential equation. That is, whenever roots of characteristic equation obtained from a second order differential equation are real and distinct, you would have a solution simply k1 e raised to the power first root times t plus k2 e raised to the power second root times t. Such a system would be called an overdamped system, as is represented by this curve. Similarly, when the roots of the characteristic equation are repeated, uh, then the response of the system will be k1 times e raised to the power first root times t plus k2 into t times e raised to the power root times t. Such a system is called critically damped system, as is represented by this graph. In case the roots of the characteristic equation are found to be complex conjugate, then the response of the system will be k1 e raised to the power real part of root times t cosine of imaginary part of complex conjugate roots times t plus k2 e raised to the power real part of complex conjugate roots times t multiplied by sine of imaginary part of roots times t, and such a system is called underdamped system and will be represented by a graph like this.